Hi everyone. In this video, I'll be covering Dalle 1. I'll be talking about its different components and implement and train it on a toy dataset which will be MNIST images on different kinds of backgrounds. I'll then try to visualize and get some insights into what exactly the model learns and looks at in order to generate images. Before we move on, if you guys are liking these videos and learning something from it, please do press the like button and subscribe to the channel so that it reaches to a larger audience. Dalle basically has two components. The first one is the discrete variational autoencoder, whose responsibility is to encode image into a set of discrete tokens and then learn to decode the image from these discrete tokens. It's kind of similar to VAE with a minor difference of how it's trained. The second component is an autoregressive model, which learns the prior distribution over the text and image tokens. So if we have a caption and an image, our caption can be tokenized using a vocabulary into a set of tokens, and the image can be encoded into a discrete set of tokens by the VAE. Then the autoregressive prior learns the distribution from the sequence of text and the image tokens. And once this model is trained, we can take a caption, tokenize it using a vocabulary, and have the autoregressive model predict the next sequence of tokens. These image tokens are then fed to our trained VAE decoder to generate an image. In our last video on VAE, we learned this prior only over image tokens using a simple LSTM. Here, we are bringing text as well into the picture and passing to the model the entire sequence of text and image tokens as one single stream to train it. The two components are trained in two different stages. In stage 1, we learn the codebook. In case you haven't seen my video on VAE, you can check it out to understand why it could be beneficial for us to have a discrete VAE rather than a continuous VAE. For VAE, for each encoder feature map output, we find its nearest embedding token and replace that with it. And since we used argmin, which is not differentiable, we used straight-through estimation to pass the gradients from the decoder to the encoder. Here, the authors used the Gumbel Softmax relaxation for selecting the embedding instead of argmin. This allows the entire process to be differentiable. Let's see what this Gumbel Softmax means and what it is doing very briefly. Imagine if you had the following two objectives. You want to sample from a discrete distribution, and you want the entire process to be differentiable. Let's make it a bit concrete by saying that we have this node which predicts the logits for a discrete distribution. And for this instance, we had the probability of 0 index being 0.6, of 1, 0.3, and of 2, 0.1. So how do we sample? We can't just take argmax because that would not be sampling. If we execute this so-called sampling attempt 1k times, we'll always get 0. But what we actually need is 0 to be about 600 times, 1 about 300 times, and 2 about 100 times. It turns out that if we replace this argmax logic instead by this piece of code, where we take 3 samples from a uniform random noise, and then add the negative log of these samples to our logits. Then when we do argmax 1000 times, we exactly get what we want. What we have done here is a way of mimicking Gumbel noise, adding which to our logits allows us to sample the points. And this is called Gumbel max trick. So great, we have sampled points according to the discrete distribution, but we still can't backpropagate. Because to sample, we used argmax. So instead of argmax, we can apply softmax. It's important to realize that we could not apply softmax on the logits, because again, for all of the 1000 iterations, it would always put the largest probability mass on the 0 index. But if we apply softmax after adding the Gumbel noise, the frequency of the index getting the maximum probability mass would follow this discrete distribution. In an actual implementation, we also add a temperature lambda to the softmax formulation. This allows us to control how closely we want the softmax output to mimic the categorical distribution. So these plots are all for cases where the 0th index has the maximum value of logits plus the Gumbel noise. In lower temperatures, softmax output would be values very close to 1 on the index of maximum value and rest all being 0. This would be then like a one-hot encoded vector. And on the other hand, when you have a very high temperature value, softmax output would have equal probability mass to all indexes, no matter what the values of logits are. So this is like a uniform distribution. So we have solved the issue of sampling as well as backpropagating. But how does this fit into stage 1 training? Now we know that during VAE, we replace each encoder output feature map with its nearest codebook vector. This is what we do here. Our encoder for each feature map pixel outputs the logits of the probability distribution of that feature map pixel over all the embedding tokens. So let's say for the feature map pixel F1, we get these k logits. These then go through Gumbel Softmax and we get a probability distribution over the k embedding tokens. You can look at it this way, that we are quantifying how similar this F1 feature map output is to the all k embedding tokens. Then we take the expectation of this. And if you have a very low temperature value, then this will land up in the regime of VQVAE because our P would basically be a one-hot vector, and we'll effectively replace F1 with one embedding token. Whereas on the other extreme, if P is uniform, then all the FIs will be replaced with the average of all embedding tokens. The remaining part is exactly same as any autoencoder. Once we have replaced each encoder output with the expectation over the k embedding tokens based on the encoder output logits, we pass this to our decoder and train using reconstruction laws. The authors also add a KL divergence loss, with the prior being the uniform distribution over k tokens. This prior basically prevents the model from codebook collapse, where only a handful of the embedding vectors get used. Once you increase the weight of the KL loss relative to the reconstruction loss, you will see more and more of codebook vectors being used. And at the other extreme, all the embedding vectors will be used equally, but then the reconstructions will be of no use. For this dataset, I had to tune the KL weight a lot, but even after that, I was getting better images without it, but maybe with a little bit more tuning and training, it would have given better results. So that's it for the stage 1 training. I'll add links in the description which will do a much better job at explaining Gumbel Softmax and get into more details than I have, but for the purpose of the video, you should be fine. Let's move on to generating our toy dataset and see some output of stage 1 training. The dataset that I create is MNIST images colored in a desired font color and placed on either a solid or a texture background. I have a pool of texture images from a dataset called Amsterdam Library of Textures. I have the number images from MNIST, and I take a pool of 10 colors. Then for each data point, I sample a resource from each of these three pools and combine to either generate a number on a solid background or generate a number on a texture background. I ensure that the dataset has a ratio of 1:3 for solid to texture background images, just because the texture images would be harder to learn to reconstruct. And I generate about 80K training images and 8K test images. The caption for these data points are curated by taking a fixed format caption and replacing the number, color, and texture words with the sample data point. Another thing to add is that I also specifically fix combinations of color and number, as well as texture and number, to ensure that these combinations are never present in my training set. So say for 4, I'll choose the color pink and the texture stones. Then my training dataset will never have a 4 in pink or 4 on a background of stones. This is so that I can test how well my model does while generating 4 in pink or 4 on a stones texture. For both the stages, I'll go over the implementation in the end, but after I have trained this VAE for about 10 epochs on images of 112 x 112 resolution, I get these results. The left image is the input and the right one is the reconstructed output. The encoder downsamples the input 8 times, so the decoder gets a 14 x 14 input, and from that it recreates the 112 x 112 image. These results are for the case when I have 2048 embeddings, with my embedding dimension being 512. You can see that there are areas where there is blurring and the output is not that crisp, and if you pass in a higher resolution image and train the model a bit longer, then those should further get refined. Since effectively VAE is converting the entire dataset into discrete tokens, where each token can be one of the 2048 embeddings, we can try to see what these tokens actually represent. For this, I simply pass in our image to the trained encoder and get the sequence of tokens, and then fetch the top 4 most frequently occurring tokens. For each of these tokens, I create grids of 14 x 14, where each cell is then replaced by that token. So for token 1, I'll create a 14 x 14 grid with all values being token 1. And for the last one, I'll create a 14 x 14 grid with all being token 4. Then their embedding representations are used, and we get 4 grids of 14 x 14 x D, where D is my embedding dimension. These 14 x 14 x D grids can then be passed to our decoder to see what that frequently occurring token represents. And we see that all the discrete VAE is doing is learning units of image. And these units are either solid, to enable the decoder to recreate regions of solid color like the blue, orange, and gray color of the numbers, or patterns using which the decoder can use to recreate textures like the green and black pattern for the second example. Let's now go over the stage 2 training. If we had to train a language model on the captions, we would have taken the words of caption, done a lookup for each of them in our vocabulary. These indexes would then be converted to vectors using our word embedding space. We would also convert the positional information into a vector of the same dimension. And finally, add them up and pass two layers of a decoder-only transformer, which is trained using cross-entropy loss to predict the next token index. If all we wanted was to generate images unconditionally, we would train this similarly just on image tokens. We would first pass the image to our trained stage 1 encoder, get the sequence of discrete tokens. These tokens would then be converted to vectors using some image token embedding space. And like language, we would also add positional information to this, and finally pass it to the transformer, which is then trained to predict the next image token. For generating images conditionally, we'll just combine these two approaches. We'll take the caption and image pairs, convert the words to vocabulary indexes and then to word embedding vectors. The image tokens on the other side would be converted to image embedding vectors. We would add positional information on both the sides and pass them together as a single stream of input to a transformer. The final output of the transformer now would have a FC layer, the output size of which would be the number of discrete image tokens plus the number of words in our vocabulary. The model would be trained using cross-entropy loss, and each token's representation would be used to predict the next token. Words will predict the next word, and image token would predict the next image token. And the last word, in our case being Seth, will be trained to predict the first image token. And that's really all to it. I will obviously go over the implementation in the last part of the video, so if some aspect is not clear now, hopefully after watching the implementation it will be. So once you train this, you will get these generation results. These are from a 4-layer transformer, and all the captions here demand to generate a 4, and moving across rows we change color in the caption, and moving across columns we change the background texture. Here all I have shown is images of texture background, just because that's harder, but it obviously does well when the caption has solid backgrounds as well. And you can see that it's generating different variations of numbers, as well as different variation of backgrounds. And moreover, 4 in pink and 4 in stones are indeed our test set points. And it does well there also, which is great. Like we did for stage 1, let's try to see more closely what the transformer looks at while generating the image tokens. So here I'm looking at the attention weights of the first transformer layer. On top left, I have text-to-text attention, where it's showing how much a word on the y-axis attends to the other words. Yellow regions mean higher attention and blue means lower. The bottom left part is image-to-text attention, where I look at the attention between the image token just generated with all the text tokens across all 8 attention heads. The bottom right part is image-to-image attention, where I look at the attention between the image token just generated to all the image tokens before it. In both the bottom parts, I have placed a threshold of 0.1. For image attention, I display the max pooled value across the attention heads as the self-attention value. The image on the top right is a random image, where I simply take a random sequence of embedding tokens and feed it to the decoder. Then you will see that as my transformer generates each token, I replace that index of the random token sequence with the actual predicted token, and then pass this sequence again to the decoder to get a new generated image. Looking at the text-to-text attention, one aspect that was coming out clearly was that the SEP token had a higher attention on the texture names, like in this case cigarette, which makes sense since it's this guy's representation that is going to generate the first image pixel. We can see similar pattern on the image-to-text attention as well, where for the first image token, we get higher attention to the texture name token. Since my images will have the number in the center, at the center regions, the model always ends up putting higher attention to the number word. And right when it's about to generate the first pixel of the colored digit, it has higher attention to the color word as well, which again makes sense. The image-to-image attention is mostly focused on the neighboring pixels, since both the texture and the solid backgrounds can be created by repetition of the neighboring pixels. And finally, you will see that even at the extreme end of the number, it has high self-attention to all previous image tokens that are corresponding to the number. It's the same on this solid colored background image generation as well. Here the SEP token has higher attention on the word solid as well as the actual background color, but the other aspects are more or less the same. While generating the first blue color pixel, it again has higher attention to the word blue and the number 1. For the later parts of the image, it limits its attention to the number word and the image tokens corresponding to the number. I also tried to see what kind of positional information was being learned for the image tokens. What I do for that is I take my position embedding vectors. My encoded image is 14 cross 14, so I have 196 absolute position vectors. I then take each, for instance, say P1, and find the cosine similarity with all the 196 vectors. So if I do it for P1, I will get 196 similarity values, and I can reshape them so that I get this 14 cross 14 image. And then I generate this plot for all the 196 position, which will give me 14 cross 14 such plots. I select every other row and every other column to display it here, and hence I get 7 cross 7 plots. So here when you move across the x-axis, you move from the left part of the image to the right part, and moving on y-axis takes you from top to the bottom. And each plot is the similarity of that position vector with all the other position vectors. This is something that the authors of VIT papers did, and I just picked it up from there. But what's interesting is that because my images have an inherent difference as far as central and boundary regions are considered, where the central regions are mostly used for generating the number and the boundary ones for texture. The model learns positional embedding vectors in such a manner that allows it to clearly distinguish these. We can see that positions in center have higher cosine similarity to all the central regions, whereas the boundary locations have a higher cosine similarity to all other boundary regions. I will now go over the implementation of the different parts. First, the discrete VAE. For the encoder, I create this list of con value blocks and increase the channel dimension and downsample as I move across the layers. Since the encoder outputs logits for the K embedding vectors for each feature map pixel, the last layer of the encoder is a 1 cross 1 convolution with a number of embedding vectors as the output channel. The quantizer will then convert the encoder output to the embedding representations. This is the part where we take the logits, and after Gumbel Softmax, I get the probabilities for all embedding tokens for each feature map pixel. It'll be 1 hot only if the temperature is very low. The third line of the forward is the place where we take the expectation over the embedding tokens using the probability values. It's equivalent to permuting the dimension consisting the probabilities to the last and then computing matrix multiplication with the embedding weight matrix. And then finally reshaping it back to match the decoder input shape. The quantizer has output channel dimension same as the embedding dimension. Lastly, for the decoder part, here the layers will be con transposed with each layer upsampling twice. The final layer will have output channel as 3 and tanh activations as our images are normalized from -1 to 1. Before calling the decoder layers, we convert the quantizer output from embedding dimensions to the input dimension of the first con transpose layer using 1 cross 1 convolution. The discrete VAE is then simply calling the encoder, quantizer, and the decoder one after the other. And it can be trained using reconstruction loss and KL loss if the weight is non-zero. For the transformer implementation, I take MinGPT and make minor changes to it. I add few fields in the config like image vocab size to create the image embedding space. This will be 2048 cross D dimensional, where D would be the hidden dimension for the transformer. Then during initialization, I initialize the image token as well as the image positional embedding together with the text token and text position embedding vectors. In the forward method, I change it to now receive text as well as image tokens. and after converting them to their respective embedding space and adding positional information, I concat them as one stream, and then like before, the model gets trained using cross-entropy loss. The Dalle class is then responsible for calling the VAE, getting the image tokens, and then passing the text as well as the image tokens to GPT. It also creates targets for the cross-entropy loss, which is just the input sequence shifted by one position. And as I had mentioned, the final layer will have output dimension as text vocab size plus the image vocab size, which is why for the targets for our image tokens, we add the text vocab size. So if my target image token is 7 and the text vocab size is 50, then I'll modify the target image token to be 57. Likewise, while inferencing, if the model predicts the output as 57, that will mean that the token to pass to the VAE decoder is actually 7. And that's it. That's all you need to set up everything and train and generate outputs. This was a very high level overview of the implementation. And also it's not exactly like the official Dalle implementation. For example, I only implement full attention, whereas the authors try out with row, column, and also convolutional type attention. And since my dataset was very simple, I really didn't have to do all the tricks that they had to do for training it. But it still covers all the core parts of implementation. With that, we come to the end of this video. If you have watched it till here, then thank you so much. And if you gained anything from it, please like the video and subscribe the channel and share it.